In deep learning, a model's capacity to absorb information is physically constrained by its parameter count. To learn more, you need a larger network. But standard neural networks face a severe architectural bottleneck. They are dense. This means that to process a single piece of data, like one word in a sentence, the network must activate every single parameter across its entire structure. Because every node fires for every input, expanding the model's capacity causes a massive increase in training costs. There is a strict one-to-one linear bond between the total parameter count, the capacity, and the flops required to process each token. You cannot increase one without increasing the other. The theoretical solution to this bottleneck is conditional computation. This is a network design where discrete sections of the model can be dynamically turned on or off, depending on the specific example processed. Decoupling a model's capacity from its computational cost is an essential engineering challenge. If researchers cannot break this strict bond, training models on trillion-word datasets will remain permanently blocked by the physical limits of hardware. To break this dense scaling limit, engineers introduced a structural replacement for standard dense layers, the Sparsely-Gated Mixture-of-Experts Layer, or MoE. An MoE layer consists of two main components. First, there are the experts, a set of independent, feed-forward neural networks. Second, there is a routing mechanism known as the gating network. Instead of passing through the entire layer, each incoming token is evaluated by the gating network. The gate then sends that token only to a tiny, highly selected subset of the available experts, leaving the rest of the layer completely inactive. With sparse routing, a model's total parameter count can increase by a factor of over 1,000 without triggering a corresponding spike in processing time. The MoE architecture solves the capacity compute paradox by holding the active computational budget, the flops required per token, strictly constant, regardless of how massive the total parameter count becomes. To intercept and route tokens effectively, the MoE layer is sandwiched between standard recurrent layers, like LSTMs. An LSTM, or long short-term memory network, is a type of architecture designed to process sequences of data over time. The recurrent layers feed into the central gating network, which then fans out to n separate feed-forward expert subnetworks. The gating network multiplies the input token vector, x, by a weight matrix, wg. This calculation generates a dense probability distribution, assigning a value to every single expert in the layer. To enforce sparsity, the system applies a keep-top-k function. A softmax function, a mathematical operation that normalizes a vector of numbers into a probability distribution, is applied, but it is instructed to isolate only the top k values, such as the top 4. All remaining expert probabilities are forcibly set to negative infinity, which causes their gate values to equal exactly 0. If k equals 4 and the total number of experts n is 2048, the system only evaluates 4 subnetworks per token. It bypasses 2044 subnetworks entirely, saving immense amounts of compute. Early in training, a purely deterministic gate will fail to explore all available experts, favoring a few paths while ignoring the rest. To solve this, tunable Gaussian noise is added to the gating equation before the keep-top-k function is applied. This ensures a statistical exploration of the entire expert pool before the network's weights converge. This specific noisy top-k gating equation enforces strict sparsity and saves compute. However, it simultaneously creates a massive new inefficiency at the hardware level that must be addressed. Modern deep learning relies on distributed hardware clusters. GPUs require large batch sizes of data, processing many examples at once to amortize the overhead costs of loading parameters from memory to the compute cores. Sparse routing creates what is known as the shrinking batch problem. When a standard batch of data hits the MoE routing layer, it is violently fractured. A large batch is conditionally routed across n experts, reducing the number of examples each expert sees to a fraction of the original size. As the per-expert batch size approaches 0, the GPU compute cores starve. They sit idle, waiting for network parameter transfers to complete. The computational workload is no longer large enough to hide the latency of moving data. The architectural solution is to synchronously mix data parallelism and model parallelism across the cluster. The standard dense layers are duplicated across all devices, but only one shared copy of each expert exists on the network. This blended topology allows the MoE layer to intercept data from all parallel input batches simultaneously. By combining these fractured inputs synchronously, the system forms a massive superbatch, effectively multiplying the available tokens before routing them to the experts. Without this specific structural blend of data and model parallelism, the theoretical advantages of sparse routing would be entirely erased by distributed hardware bottlenecks. Even with sufficient batch sizes, routing networks are prone to a catastrophic failure mode known as expert collapse. This is a self-reinforcing loop. A gating network routes slightly more tokens to one specific expert. That expert trains faster and becomes more accurate, which biases the gate to send it even more tokens. The remaining experts atrophy from disuse. To prevent collapse in a model with over 100 billion parameters, structural regularizations, specifically auxiliary loss functions, must be injected directly into the training loop. A loss function is a mathematical penalty that tells the network how far off it is from its goal. The first is an auxiliary loss function called L-importance. It calculates the sum of the gate values across all experts and heavily penalizes variance. L-importance forces the gating network to assign an equal aggregate probability weight to all experts across a given batch of data. However, equal probability weight does not mean equal physical memory load. An edge case can occur where one expert receives a single token with a massive gating weight of 1.0, while another receives 100 tokens with tiny weights of 0.01. The probabilities are mathematically balanced, but the physical hardware processing the 100 tokens crashes. To fix this, a second auxiliary loss function is added, called L-load. This function is designed to estimate the discrete probability of token assignment and penalize variance in the actual physical distribution of tokens. L-load prevents out-of-memory crashes on individual GPUs by ensuring the physical token count routed to each expert remains strictly balanced. L-importance and L-load are not optional optimizations. They are the mathematical guardrails that prevent a massive distributed MoE network from cannibalizing its own hardware resources. This chart plots test perplexity against the computational budget for the 1 billion word language modeling benchmark. Perplexity is a metric evaluating how well a model predicts a sample of text. Lower perplexity means a better model. At a strictly matched computational budget of 8 million operations per time step, the 4096 expert MoE model dramatically outperforms the dense LSTM model, dropping test perplexity by 24%. This chart shows what happens when the sparse architecture is scaled to a massive 100 billion word corpus. The lower line tracks the perplexity dropping continuously as the parameters scale toward the 100 billion mark. The test perplexity plunges as the expert count scales up to 65,536. At this point, the system is operating as a functioning 68 billion parameter model, vastly outperforming dense baselines. As these sparse models train, a critical emergent behavior appears. Without any human direction, the routing network naturally organizes the experts into highly specialized syntactic and semantic clusters, with specific experts activating only for distinct linguistic contexts. The empirical data isolates a clear fact. Decoupling capacity from active compute breaks the traditional scaling laws, yielding continuous improvements at a fraction of the expected processing budget. Efficiently training a 137 billion parameter model in 2017 meant structurally bypassing the hardware bottlenecks of that era. This specific sparse routing blueprint became the bedrock for scaling modern architectures. In 2020, Google introduced G-Shard, utilizing MoE layers and automatic sharding to scale conditional computation beyond 600 billion parameters. A year later, the switch transformer milestone simplified these routing algorithms to finally breach the 1 trillion parameter threshold. By identifying the mathematical constraints of dense networks and engineering strict solutions for sparse routing, batch starvation, and expert collapse, this architecture laid the exact foundation for the trillion parameter AI models used today.